And if you're saying, can I now hear you? The answer is still no. But I'm just putting words in your mouth. So if you're now laughing in frustration about Linux audio, then we are all sympathetic, but cannot hear you.
Is that directed to me?
No. This is Eliza's hilarious audio problems, not your hilarious audio problems.
I should have known that. I should have known that I have actually plenty of time. Like, I actually only need to outrun the bear here.
Is it Mel Brooks who's like, tragedy is when I cut my finger, comedy is when you fall down an open manhole and die? I feel like there's something very similar to that with regard to audio issues.
Linux audio? Yeah.
Like when it's happening to someone else, it's hilarious.
It is hilarious. You know what I would also liken it to is like, and I don't know if you're the same way, Adam. I am at ease when I am on a flight and a infant or toddler is losing its mind. It calms me. It literally calms me.
It's so true. There is, I think, for every parent, right? Like before you have kids, when there's a screaming toddler or screaming child on the flight, you're like, God,
brother,
get me out of this situation.
Yeah, totally.
And then
Exactly.
when you've had responsibility for a screaming child on a flight, and then you go on a flight and it's not yours, you're like, that's fine. Like scream all you want, kid. Like I don't have to do anything.
And in fact, it actually makes me feel better because I mean legitimately, because I feel that there's a karmic debt that I incurred with my own screaming toddler. I'm sure you had this happen. My now 20-year-old when he was 9 months old, screamed the entire flight from Chicago to San Francisco, and then we finally get into like final approach. We've been cleared to land. We're over to the San Mateo Bridge, and the kid just falls asleep. Are you kidding me?
Yeah,
joking.
You might younger one was never much of a screamer, but you will enjoy this on a flight to Amsterdam. Like he would scream if you stopped moving. So on a flight to Amsterdam with him, I walked something like a mile just doing circuits on the airplane.
You also see, like, you see that too when you're traveling. You see some parent. Oh, could I assume like a year and a half old, something like that? Was that the age?
Yeah, he was like 11 months or something like that.
But yeah, right. When they're like, he's like, he needs that mobility to just for his own sanity, and you just see like a parent just doing laps on a plane, and I get it. It just like it fills me up. It calms me down.
He made so many friends on that flight because everyone saw him 35 times, including one person who was like, "Can I feed him a peanut?" And I'm like, "This is not a petting zoo, right? This is not like there are many reasons why the answer is no, but it's not like leaving." At that age, the answer was no.
You are no on foreign peanuts.
I think
you
peanuts
were
a no
peanut.
before. I think for a variety of reasons, peanuts are a no before one. I guess maybe not.
I think you also have to ask the follow-up question, like, do you have children? Because if they have children, then you can be assured that it's not a poisoned peanut. If they do not have children, the peanut might be poisoned, actually.
I wasn't that worried about a poisoned peanut, other than like, he had never had a peanat before. So other than the like intrinsic poisoning qualities of peanuts.
What better time to experiment with peanut allergies
than over the Atlantic? Yeah.
There's got to be an EpiPen on here somewhere, right? Well, there's not. There should be. I think we can all agree with that. There should be.
Yeah,
it's
for sure.
Testing in production.
There we go.
Would I be correct to assume that you can hear me, but it sounds bad?
You sound faint.
Adam's a critic. I think it sounds fine, but yes, you should. I think it sounds fine.
Okay, well, the fancy USB mic has refused to talk to Pipewire for obscure reasons, so we're stuck with this.
In that case, you sound more than adequate.
I would just like to point out that during the last iteration of the debugging call that we're about to discuss, my mic didn't work at all.
Yeah, no, there's definitely something to that. A kind of a karmic balance that must be achieved. That we can have functional systems or functional audio, but actually not both of those to actually.
Well, and I don't know if this is a spoiler, but don't forget that Meet failed. Google Meet had an outage in the middle of all this debugging as well.
Did have an outage. Yeah. Oh, yeah. That is which is not. I mean, that's a kind of a first. I feel like that was very surprising. But yeah, that was. It was definitely an adventure. And maybe that's a good segue, Dave, into kind of how I kind of want to tell the story of how we got here. And Augustus, it really starts with you and you noticing. So for those folks who've been following the company, you may be aware of this, but for those who are not, we have our own Oxide rack that is in production. We've got an Oxide rack that we use that is in like development that we affectionately call dog food. That is like constant. That looks like a dog's breakfast. Actually, at this point, it's really not. We used to show that off to like potential customers come by the office, Adam, and now it's like, I don't know. It's like people are like, is there a Dell Optiplex in there? I'm like, there is, but that's. I mean, let's not look at that. That's for $100 on eBay. Like you're focusing on the wrong thing here. There's this, so we've got our own kind of engineering system, but we also have taken a production Oxide rack. I mean, and actually, technically not very close to production PVT build, and we stood that up ourselves in an actual proper data center, not in our office here in Emeryville. And then we use that for people to. It's a great way for people to try the Oxide rack, which is terrific. We can spin up a silo for them, and then we use it ourselves for our own infrastructure. And Adam, dtrace.org. If you go to my blog anyway. Is your blog on the Oxide rack yet? Why are we doing this? I realized this came across as pointed and I really didn't intend it that way. Let's just say that some blogs are on the Oxide rack and some others have made different choices.
Yeah. Don't worry. I'm editing all this out anyway.
There you go. No, but we use it for our own infrastructure, and it's a lot of fun to be our own customer. So, Augustus, you noticed in what we call colo that it was not performing very well. You were starting to see something. You'd seen what felt like a regression in performance.
Yeah, we had just performed an update to our latest release candidate, so we were worried. All right, did we introduce something new that's causing latency on certain requests? And I got pinged by multiple people. So there's multiple people across the company started to notice it. So it was definitely let's start looking at this immediately type of thing.
Right. And what did you start to discover?
So we had a couple things going on. Post the update, we had been running some disk removals. So that's a background process that ended up causing like a decent amount of database strain.
And actually, so we're just explaining. I don't want to go tangent about why we were doing that. Actually, it's kind of interesting.
Yeah. So we're going to compliance. More compliance. Compliance testing we need real running hardware that's all like fully functional and working. So we're testing sled removal to move those over to a compliance rack.
So compliance is for like electromagnetic interference. So we ring that favorite chime of ours when we point you to the Oxide in the Chamber of Mysteries, where we did our initial compliance run, but we are now making the Oxide rack available for sale in other countries, and that requires there are different regulatory regimes in Europe and Japan, for example. So we need to do another compliance run. So that's
Right, so we take these, we remove one sled at a time, just so we can make sure, that things look healthy. So remove a sled, it triggers off a whole bunch of tasks, which, so that all runs automatically when the sled gets expunged. We thought, are we causing too much database contention based on the load coming from replacing disks? But, so we take a look at our, logs from there, we see some errors around database access. So these sagas that run in the background that repair disks are starting to fail to get database claims. And that's probably where our journey starts. We start looking at, why can't we talk to the database? And I think this all eventually stems from that.
And Augustus, at what point are you like, there's something amiss here? Or maybe you were already past the point where like, something is not right. We need to be investigating this.
Yeah. So the first thing, as soon as we start seeing latency, we know like that's never good. That's always like a major indicator. Seeing the logs say that they cannot acquire a claim to the database, or essentially a handle to the database, is always going to be bad. That means multiple things across the system are failing. The system is resilient to that, right? It can keep moving along, but we need to know what introduced the condition that made that occur. What we spent a bunch of time looking through our database. So like obvious things are like, are all of the database copies running?
Right.
Does Nexus have connections to all of the databases? Are they running out of CPU or memory? Like our initial looks though, none of those all looked fine. Like all nodes were up. All of our control plane had the expected number of connections to all the database nodes. We weren't running high on CPU or memory, which puts us in a really interesting case of, well, if the database is fine, then why can't we talk to it?
Right. If everything is fine, why does the system suck?
And just a couple of definitions. We got Nexus, which is our kind of orchestration software running the control plane. And then when we're talking about the database, we've got Cockroach DB. And how many shards do we have? Is it 5?
Yeah.
Or how many copies? Yeah.
Yeah, it's a 5-node cluster with replication factor set to 5. So everything goes to all 5.
Sweet.
And so, I mean, a reasonable thing to check is like, how is the database behaving? I mean, we're kind of beginning to back up. We are complaining about not being able to get a database handle, and the first thing you want to be sure of is the database functional and is it operating at a latency at which we expect?
And that seemed like the most obvious answer. So
yeah, and but that seems fine. All right, the database seems fine. And how are you actually, Augustus? How are you determining what the database's responsiveness is?
So it's mostly like your standard debugging tool, like just going into the actual database. So we'll, connect to one of the Gimlet hosts, go into one of the Cockroach zones, and see like how many connections like do we actually have outstanding to this thing. We can also look within those zones and those slides to see like if those are running, if the memory or CPU is particularly high on those. And then we also verify that we can reach all 5 nodes from each of the like Nexus control plane zones to make sure like we haven't lost network connectivity for some reason throughout there.
And Dave, when did you swing in on this? Is kind of about when you were swinging in on this problem?
I swung in early because the first problem we first noticed this when we did the expungement because we were having all these Saga failures because of this claim error, and we were getting a whole bunch of other scary stuff from Steno that is mostly unrelated, but I spent a while digging into that. And then it seemed like that was fine, so I kind of stepped out a little bit and came back in, I don't know, 20 minutes later when we started digging into the console latency problem, which is, I think, really what we're talking about. And there were, I don't know how much you want to dig into all the blind alleys we went into as well. I mean, there were several, even at this phase, a lot of them pretty short, but like we had a change in this release to the way that we stored session tokens, like the table that stores session tokens. And so there was a point early on where we were like, and it had affected the schema migration because we found that the table was really large in this particular deployment. And so one of the first things I thought did we screw up the indexes on this somehow? And these queries are taking forever and they're occupying all the database connections. And that was very quickly not the case. But, there were a bunch of stuff like that came up early.
Okay. So what's next? Because at some point we exonerated the database by looking from the Diesel side and actually looking at our query times.
That's right. And I don't remember the exact ordering of things, but I think it was relatively early that we went and looked at, so one of the things we did relatively early with the database integration, I think this was work that Sean did, was add dtrace probes to, sorry, maybe this was Ben, the points where we are executing queries. So we're using Diesel to execute a query to the database, and we have start and done, and we have the actual SQL as well as the SQL bind parameters, so we can see what's going on. And that showed that there wasn't anything that egregious. So the way I would characterize the problem at this point was that if you like refresh the console page, which makes a whole bunch of HTTP requests to fetch all the files and stuff like that, many of those requests would complete very quickly, and then you would hit some requests that were taking like 8 or 9 seconds, and so you'd be sitting there watching it like not complete, and then all of a sudden like a bunch of those end up completing. So, yeah, that was what it looked like, and then we weren't seeing any database queries taking anywhere near that long. I think the longest we were seeing was in the 500 milliseconds to 1 second bucket, which is, it's a little hard to see how that turns into an 8 or 9 second HTTP request.
And we were seeing very few of those. I mean, as I recall, it's like we were really not seeing, when I was looking at it, it was like, outliers at maybe hundreds of milliseconds.
That's right. It was like 1 out of thousands that we traced, and that included that whole period where several requests had taken a long time.
And this is just a quick aside on this, because I think this ends up being very load bearing for the stuff that we ended up doing later on this problem. So you mentioned the Rust USDT crate, which I believe we also talked about, Adam, in our dtrace at 20 episode. But this is the work, if not other episodes, I feel like we must have talked about that a couple of times, but this is, work that has been just absolutely essential for us. Do you want to just describe that a little bit? Because what you were using, Dave, you were using the USDT probes that we had built into the system that allowed us to really, like, we want to know how long our query is taking in terms of like a query. And those probes were really critical for exonerating that part of the system.
Yeah, in terms of the USDT provider or probes in Rust, that was something Ben Necker and I did like 4 years ago or something like that. Certainly, like shortly after he arrived at Oxide, and I think not to give the whole history of USDT, which we've done several times and at length, but I would just say that like each time we have brought USDT to a new language or area, we've gained even more religion about the utility of it. So, we made it so that it was pretty easy to drop in probes, so that it would be compiled into your Rust program, and then after the fact, on a dtrace enabled system, you could dynamically instrument them and see what was going on. And I think the one weird thing, or particularly weird thing, that we did with Rust was we used is-enabled inserti and then JSON processing within the kernel's dtrace capabilities to be able to transmit complex types from your userland process in Rust into the kernel. And it's sort of awful, but sort of elegant glorious at the same time. Yeah.
You're obviously you're fishing for the obvious thing. It's glorious. Come on, it's glorious. Well, it's not awful. It's glorious.
Well, it's got surprising effects. Like if you don't tune your string size appropriately, the JSON implementation of the kernel is sort of permissive. And it's like, well, I never saw a closing brace, but I don't know. I did my best. And it's like, well, your best wasn't good enough because you didn't find the things that I was interested in, and there was no error message. So there are like corner cases like that, but by and
Adam,
large, it's
great. As a great man once said, we view the Oasis as half full.
That's true. What a legend.
What a legend. Whoever said that was a line that Adam had. What were we talking about when there was someone who was...
We were talking about the CPU performance counter probes in dtrace that someone was adding. And I think, CPU performance counter probes were pretty awkward in terms of how they wedged their way into dtrace. And I think someone was like observing some of the deficiencies. And we do view the Oasis as half full.
That was your observation. It was very astute.
It kind of ended the conversation.
It did end the conversation. It's like, okay, well, you're obviously not interested in my feedback on on the way that the Oasis could be improved. It's like, do you want the Oasis or do you not want the Oasis? Look, next food, gas, 110 miles. You can keep walking.
Right.
But this has been really important. And so, Dave, you were using this to be able to, and using the Diesel dtrace, because is that a crate or an option in Diesel? Have we done that in? You dropped a link to the actual repo.
I need to double check. I think it is. It's definitely not just an option. I think we created a crate that I think implements the Diesel connection trait.
Got it. Okay.
And then it wraps some other connection trait impl. So you can use it to basically wrap any other kind of connection, and it will just instrument that one.
I think it's basically kind of like an interposer. Is that right, Dave? I think I've been in that code in the past, but
yeah,
just kind of sits.
Right.
Yeah.
And so based on that, it's like, this does not seem to be the database.
That's
what was next? What was Augustus? I'm trying to think. What was? I think we were just.
Yeah.
It felt like a lot of time kind of wandering around. We were not able to figure out what was going on.
So we were like fairly confused at this point, but we did know that we could at least look at an individual request and figure out what which control plane endpoint, what Nexus instance was handling that.
Yeah.
So our next clue was like, okay, let's just like, what is Nexus telling us in the logs? Where are we spending our time? Which is probably that's where we got to like the first mystery of. So we have a log entry that occurs when any endpoint finishes result, or whenever a handler finishes running, and it admits how long that handler took. So we clearly saw handlers taking 8.9, 9.2 seconds. But when you look at the actual logs that were emitted during the handler, the time between the first log and the last one is 100, 150 milliseconds, and we have essentially 8 or 9 seconds of unaccounted time.
Unaccounted time, right?
We don't know where it came from.
And importantly, it's all at the beginning of that request. That actually told us that those 2 data points told us kind of a lot, right? Because you can definitely see problems like this if there's a client problem where it thinks it's made a request, but it hasn't, or it's gotten stuck in TCP hell somewhere, and the server just doesn't get it for 9 seconds. That wasn't happening because we were reporting on the server that it was taking 9 seconds. And then the fact that it was all in the last 120 milliseconds meant that, including, for example, the auth-z stuff, that was all happening at the end, meant that it wasn't like we went off and did some database query as part of whatever this request normally does, and that was taking forever. It was like something was happening in some, unfortunately, invisible part before all of that.
So request comes in, and then nothing happens for kind of an awkwardly long amount of time, and then we do our first thing, which is to validate credentials. Is that right?
But yeah, that's right. I think, I can't remember if authn probably was that. Yeah, I think that's right. I think that what you just said is exactly right.
Gotcha.
So pretty frustrating, to put it mildly. And then Dave, and we at some point we are definitely wondering about that. Because there are parts of the system we just can't see into, and one of the parts that we had some visibility but not total visibility into was Corb. Do you want to describe that a little bit and kind of our as the thinking was evolving about where this could be happening?
Yeah, so a little bit about Corb. So Corb is a connection pooling and service discovery crate that we built. It's inspired by something we did or some of us worked on at Joyent called Qball, and it's all about doing the service discovery and connection management for high availability and scalability, within a data center. So this is not like external service discovery and load balancing, but this is something that we have started using in a bunch of components and will probably start using in all of our components as a way of it takes things like the DNS requests to do the service discovery and the connection establishment out of the request hot path by doing those things in the background asynchronously, and then you ask for a connection and then you just get one, and it's a standard connection pool in a lot of ways. It's just doing a lot of that stuff asynchronously outside of the request path. And the error message that we actually got here, that we saw this at the beginning, was failed to access DB connection. Backends exist and appear online, but all claims are used. And so that was why, naturally, certainly when I've seen this kind of problem in the past, it's the database that's the problem, because if the database does get slow, that's what you see. You see all these things backing up on this very limited resource, which is the number of connections available to it. And I guess you could kind of go back further and say that, like, when working with traditional relational databases, connection management is really important. They're an expensive resource on the server, and they're very finite. And a lot of traditional databases like Postgres don't deal very well with overload, and so you need to not overload them by not having that many, by not asking it to do very many things at once, which is part of this connection management stuff. And so that's why we have this limit. But now that we're hitting it, we're like, okay, what does this mean? Especially once we've exonerated the database. That kind of led us naturally towards Corb because, it certainly started leading to questions that we wanted to ask Corb, like, well, okay, if the database is completing these queries quickly, but claims are not available for clients to use, what's going on with those, and like the specific questions that we wanted to be able to answer, eventually. I don't know that we quite formulated these right away. We're like, how long are things holding these claims for? How long is it taking them to acquire these claims? And sorry, I forgot what the last thing I was thinking of.
And we were able to get to some of this stuff, but not all of it. We were kind of missing some of the. I mean, it's not. This was not without instrumentation by any means, but we didn't have quite a complete enough picture to fully exonerate Corb.
Yeah, that's right. And the third thing I realized was it's how many connections were available at any given time. Because the assumption, if you're in a situation where the database is the problem, then what you would expect to have is that all of the connections are in use all of the time, right? But because the database wasn't the problem, the next question was, well, do we have enough connections? Or is Corb for some reason not returning these connections or making them available to people? And so how many connections are actually in use at any given time? If that number was less than the full number, which was supposed to be 16, I think in this case, that would have been very suspicious. And eventually we were able to find out that it sure seemed like that was the case.
Well, and I think it's very tempting to be like, oh, okay, well, there are only 16 connections available. We're obviously running out of them. Like, double it to 32. I just feel like, I mean, we've all had experiences where someone in the room is like, let's just double it and let's push that into production.
Right, and we definitely asked that question. And the observation was like, well, we've never really the Cockroach is definitely a lot better than a lot of traditional databases and stuff like that. And it will refuse things when it's like, I'm overloaded right now. I can't serve this. But we haven't actually characterized what's safe. So what you don't want to do is just like bump all those limits way up and turn all these failures into much worse failures, much worse latency, for example, because all database queries are now terrible. That's basically why we didn't just do that.
Well, and I also felt like we didn't have the evidence that because we were like, okay, so if we're running out of connections, we should be able to see that. We should be able to see the number of connections, and we should have yes, we're running out of all of them some of the time. We should be getting close some other fraction of the time. And it's like we just weren't able to find the evidence to support that any of that was happening.
Right. Yeah, that's also a pretty good reason.
Yeah, there are some circumstances where just treating because it's easy to treat is fine. But this is one where, let's say you had doubled it and the problem had gone away. Well, then we'd just be still wondering, well, is it gone now? Is it gone forever? Like, totally. How far down the track did we push it?
How far down the track did we push it? If it had gone away. What is really scary, knowing the root cause, is it's actually completely conceivable that it would have gone away for completely unrelated reasons.
Totally.
And we've got a system where it's like, if we were to make that change, I mean, one of the nice things about Colo is it's a production environment. Like, we're not just going to slap something on there. We are going to make the change and vet it properly. It's going to go into a release. That release will happen some number of weeks later. And I mean, this is we won't know for weeks whether it has resolved the issue. And that all the more reason to be like, what more information can we gather out of the system? And as we were looking at it, it's like, this doesn't add up at all. That's the wrong direction. And it felt like it just felt increasingly like something is amiss at somewhat of a deep level, because it just doesn't feel like any. Dave, I don't know what your take was on it, but it's just it just doesn't there's a huge amount of missing time here, and either something is going wrong with the way that Corb is scheduling claims. I think that was a reasonable, I wouldn't quite call it a hypothesis, but I think kind of questions to ask is, what was Corb, what was were we processing claims in a timely manner, or was there some way for something to be queued somewhere and have to be picked up asynchronously? And that's where we had enough instrumentation. We had instrumentation there, but not quite enough to be able to say conclusively that no, Corb is definitely not the issue. And I mean, I think at this point, I guess I'm trying to kind of replay it, but at some point we get to whenever you're debugging something, you get to the point of desperation where it's like, okay, now we're like, does anyone have any ideas? Does anyone know any jokes? I mean, you're just what's kind of try anything. And Adam, it is a reminder of the greatest podcast that we never recorded on the TLB speculation issue that we found with AMD.
So good.
And although I feel like we did hit on this in the C-SPAN for debugging episode.
Don't you take this episode away. We're doing this episode someday. Don't you say, now that I've mentioned a teeny bit of it.
I thought you were jumping all over me because the need for a chime. You're just like, out of chimes. No, you gotta, there are a limited number of chimes. I can't just ring the chime all the time, pal. I'm not some
I'll ring the chime. That was a good one. C-SPAN and debugging. I was into that one. But what I mean is, we are sitting on a banger of an episode with that TLB speculation. I've been angling for that one every week for the last 2 years. We're going to do it. So don't give people like the shorthand version and then tell me, we basically did that episode.
We basically did it. Ring the chime for this episode. Yeah. Okay, look, I hear you. But that was a good example of one where we got like desperate and you're just like, okay, yeah, any suggestions are just like, any suggestions are welcome, basically.
Yeah. Well, just to be clear, and this is a little bit of a teaser for that episode, I think you said, are any suggestions welcome? And Dave and I said, I don't know, VM bug? And you proceeded to explain to us why that was the dumbest thing you'd heard. Dave, am I misremembering?
I don't think you're misremembering.
Anyway,
unfortunate.
It's going to be a great episode.
I could jump in front of that one a little bit. I thought if I interjected myself quickly enough, I could. All right, well.
No. But yeah, okay. Apparently, you've learned from that lesson, and now real dumb ideas are really welcome.
This is why we actually record every meeting, so we can all go back to that. And actually, I think you're being a little reductive, but yes, I understand what you're getting at, and I don't disagree.
Got
it. You need not cue the recording for me. It's
good. I wasn't thinking about that at all. What are you talking about?
That's right. But and in particular, I mean, Dave, now we're just kind of brainstorming, like, let's gather all sorts of information about the system.
So Sean had the good idea of, he worked on Corb and was like, we have some dtrace probes in here. And that's when we started tracing things like there's claim start and claim done. And that gave us the distribution of how long things were waiting for a database claim in the first place. Something I didn't mention about the errors, and I don't know, I'm not sure if this was probably not obvious, but we were seeing some explicit errors, but we were also just seeing latency, and we were mostly tracking the latency. The difference is that the policy of this pool is that if something is waiting for 30 seconds or something like that, then the latency turns into an error. So most of these were... So I guess what I'm getting at is the error message pointed us in this direction, but it was latency that we were tracking because by this point, the instances we were dealing with were not that bad enough to turn into errors. So we were looking at the latency of claim acquisition, and we also were looking at how long these claims were being held for, which are actually two different probes. I forget what they're called. It's like handle claimed and handle returned or something like that. And they had sort of a similar, how to describe this, the high endpoints were the same. Like we saw some claims we saw one claim held over 8 seconds, but we would see like 30 things blocked for 8 seconds, which is pretty surprising, right? I mean, there's at least hundreds of other claims being made and claims being held for much less time than that, and it's conceivable that that stuff had been queued and that those connections were all busy, but it was pretty surprising to be like, how can 30 things have been blocked on this one claim when we're supposed to have 16 connections to this thing? And that's when I think we started trying to trace the number of claims outstanding at a time. And so we were doing that with some of the same probes, but the problem was that only gives you a relative difference. Like you have an integer that you can increment and decrement. That's like how many connections do I think are used to the database right now? But you don't know what the starting point was, so you don't know really how many are in use. But we had some way of correcting for that. I forget what it was, and we found that there were only ever like 9 connections in use, and that wasn't most of the time. Most of the time there were like 2 or 3. And so that just is definitely putting together an alarming picture, particularly around Corb, which is like, why are things waiting so long for a connection when there should be more connections available? And there's definitely not enough there are multiple reasons to believe there are more connections that should be available. One is that the policy should allow many more, and the other is that only one of them is actually in use, and we know there's a whole bunch of them available. There are a bunch of them established.
Yeah.
But the one of the tough things about this. So just continuing down that path. The next thing I want to do is figure out what code path is making these claims, particularly the claims that are blocked. Well, both the claims that are being held for a long time and the claims that are being blocked, right? Because that will tell you what is logically blocked on what, right? And that might, that'll confirm that it's the HTTP request that's blocked, and it might also tell us, like, why is this thing holding a claim for so long? And unfortunately, this is where the Rust async stuff really starts to bite us. Because these things are happening. So many of these events are happening in different tasks than the ones that are actually doing the work. And so, the usual approach here would be in dtrace to grab a ustack at the point when a claim is acquired or returned to the pool or something like that. And those stacks were not useful in terms of telling us what part of the application was using those things because they were happening in a different task.
Dave, is this when you start asking questions that start making me pretty uncomfortable?
That's not a loaded question at all.
I'm not sure at exactly what point you started feeling uncomfortable.
Oh, well, I started feeling uncomfortable a while ago, but that's aside the point.
Yeah, I mean, this is definitely the line that led us to wanting to say things like, if we could know what Tokyo task it was that was doing these things, that would help a lot.
Yeah.
So, when you're using dtrace for a threaded program, it's a common pattern to be like, I have event 1 that happens to thread, and I set a thread local variable, and then some event 2 happens, and I have a probe conditional on that, and maybe I collect some more data, et cetera, et cetera. But with tasks in Rust, there's not a great way to do that with dtrace because what the things you have are probe points, and you have information about what thread you're on, but the thread you're on is changing what task it's running constantly. Sorry, is my audio getting worse, or is it just continuing to be a little quiet?
It's
You
fine.
sound fine.
Okay.
Your audio is great. We're all just basking in the image that Adam dropped in the channel of the C-SPAN for debugging, which is, I mean, Adam, it is. I not to take anything away from your physics simulation, but I really do think it's your finest work.
I think it took longer than my physics simulation.
That makes you feel so much better. I also just love. I mean, it's your facial expression on there that is the chef's kiss. I think your facial expression of just
like, what the fuck is going on?
What's going on? Like, this is nothing makes sense right now.
Yeah.
Sorry, Dave. Where were we? We were making Eliza feel increasingly uncomfortable.
Oh, because you're asking awkward questions now of Tokyo, Dave. And
of Tokyo, yeah.
Right.
In particular, Dave is asking questions like, is there a way to figure out what task I'm in when like these different like Tokyo internal functions are on the stack? And the answer to that is, well,
Do I need my lawyer?
You see, there, well, you see, it's so there's like all of this stuff going on involving like type erasure at runtime, and it's sort of like if we had gone back and added all of this instrumentation to Tokyo when you compiled this binary, maybe, but a lot of this information, you can't reconstruct because it was known at a point in time that is no longer now. So it's like you start answering these questions that are
I just love Eliza. I love your bedside manner. You're like, is my program dead, doctor? Is that you?
Well, what you really should be asking is, should we have treated the program for this disease earlier? And the answer is emphatically yes.
Emphatically yes. That the time to treat the disease was at a time that is not now.
Right. And Dave, is it fair to say that part of it is like we've spent so long debugging this multi-threaded programming model that has kind of been a big deal for the last 30 years of computing. And there's a lot of dtrace orientation around it. There's a lot of debugger orientation, not just MDB, but lots of debuggers orientation around it. And we're sort of good at knowing, okay, where is this thread right now? This other thread is blocked. Where is it right now? And when you get into the async model, the Rust async model in particular, you've got these little state machines whirring away, but we do not have the same corpus of experience in terms of how to infer state about the system in this kind of new system, that looks and feels a lot and operates a lot like this multi-threaded system, but it's quite different.
Yeah, well, and this actually, Adam, dovetails in with a Cliff Bevelism that I really like, which is the program counter is a very important piece of state.
Yes.
And it is very nice to know in a system, where is everybody right now?
Yeah.
And the problem is in an async system, you've got there are other actors that know where these things are, but they've kept their state in a way that you can't get to it.
That's right.
And
you make some program counter plus a stack pointer, man. That's big. A lot of state all of a sudden.
I think it's important that like the program counter and the stack pointer are architectural state, right?
Right.
And
Right.
in the async world, all of this sort of additional information that you want is something that exists in the user space software that you're executing. It's in a library. And with work, you can pry that information out of the library, but it's not sort of like inherent to the x86 CPU. There's always a stack pointer. There's always a program counter. You can go and look at those things because they're like part of the world in which we live. It's just sort of like something that the program happens to be doing is what's interesting to you.
Yeah, I would only say point, which is like the OS knows about threads and the stack pointers and things, and so these debuggers already know about all these things. But it's a harder problem because all of these things in an async program are just like properties of the application-specific structures in the library that's doing that scheduling. And so it's intrinsically harder, I think. Every debugger would have to know about every userland scheduler and its data structures and where it stores things and things like that.
For sure. Yeah, it is harder. I mean, and you're going to have semantics at user level that are going to be specific to that kind of runtime. And it's just, when you're introducing this layer of indirection, it can be very powerful, but can also make it really hard to understand what the system is actually doing. So Dave, you're trying to piece together what's going on from a Tokyo perspective, and getting the disconcerting news from Eliza that the time for that information was when it was being compiled. It is not now. Where you're trying to go through kind of a production binary and like, can I piece together this information? And this is a great strength of Rust, is how much it knows at compile time. But a challenge for when we want to debug these systems is there's just fewer artifacts in that production binary, and some stuff that's like, it's just gone. A program does not keep track of that state, and you do not have an easy way of getting to it.
Yeah, totally. So I think the questions at this point are basically, what is taking so long? What is the thing or things that are taking 8 or 9 seconds? And what is the dependency between the HTTP request we're trying to complete and those things? Right. And both of those were kind of hard to answer. And, we started from the probes that we had in the components that we had. We were able to exonerate some stuff. We're able to maybe not indict, but like have an area where we wanted to ask more questions. And but a bunch of the techniques that we normally historically have used to try to figure out context were just not working. And so what I ended up resorting to was actually kind of helpful was I used the PID provider to trace all the entry and return probes in Nexus for functions that had Nexus in the name, because it was too much. I didn't want to trace actually, I think I tried tracing all of them first, and then I narrowed it down. Just to have I think I used the ring buffer policy in dtrace to get...
Oh, there you go.
Because I was basically like, okay, so if I can basically exit my dscript at the point where we have just been off CPU for a long time, then I can go back and figure out what were these things doing before that. But at this point, we still did not have...
This is super hard. Oh my God, this is super hard. Because what you're trying to understand is it is so hard to debug a system where it's like, okay, I know, like, I was just conked out. Like, I've not been running for a period of time that is too long. And you want to answer the question, like, what the hell was just going on in this system? And that can be really, really hard to ascertain.
Yeah, you mean like, up until this moment, like what happened? What were the last few events or whatever that
because
occurred?
It's like, it wasn't you. I mean, this is the part of the problem is you're like, no, like all I know is that like I came to in this gutter. I don't know how I got here. My last memory is, going to the bar and here, and like I'm trying to piece together what happened and who did what to me. It's like, well, you were actually like, you were unconscious for, I mean, it's like, you know, this is like the hangover for programs. I don't know. There needs to be, you know.
This is a little bit neither here nor there, but have you seen this thing Magic Trace from Jane Street?
Yeah.
It kind of like scratches this itch a little bit. It does have like non-trivial performance overhead, but I think it basically builds a ring buffer of branches taken, and from that you can infer kind of where have I been. But I think it's Intel only. And I've never used it, but it seems really neat.
Yeah. And Dave,
anyway,
did that bear any fruit?
That particular thing I think was helpful later. I think most immediate next step at this point was we used the Corb probes that we did have to track basically everything that was happening with all of the Corb pools in the process. So all the claims, all of the what I mean is claims from the pool's perspective in terms of when things are, like how long it takes for acquisition, and then all the returns. And basically just like dumping it all and trying in the descript to keep track of how many connections we thought we had and what was still available, and lining that up with I think it was a speculative detrace speculation. Was that?
I think before we were doing that, I think I ran my first state map before we were doing that. I think
that could be the thing I'm remembering is. So this may have been before we were using speculation, was basically being able to dump out like that we had been off CPU for a really long time.
Oh, got it.
Came back, okay. And then looking back at all the Corb activity. And what that showed, which...
so maybe you're using speculative tracing for that as well. You know,
I think I was, but I'm not positive.
You know, I should assume that speculative tracing was only used once in debugging this problem. It's used very frequently to debug many problems by many people.
Yes.
The order here is definitely a jumble for me, but this, what I wrote in the thing was this was like at least smoke, if not fire, because what we saw from this output was that it was a sequence where, so, you know, we were at some steady state where like I think all the claims were not taken, and then we went off. We took a claim and we did a whole bunch of work, and then like 30 claims came in, and were not satisfied, and like that's over 10 seconds, and then the first thing finished, released its claim, and then we saw a bunch more claims get satisfied, and that was really weird. Right? I mean, that's consistent with everything we've seen so far, which were even telling with the bias of knowing what the problem was, but it's very suspicious, right? Because you're like, you have all these claims and you didn't satisfy them for many seconds, but you also didn't make any new connections. We could see that no new connections were made, and yet it was able to satisfy it with all these other connections. So I think it was around then that you were starting to do the state map stuff.
Yeah.
Do you remember?
Yeah, I mean, and this is kind of an act of desperation, honestly. So and this just reminds me of problems we've had in the past where the system, you've got a lot of different kinds of things in the system, and the system is adding up to one that does not function, and it's hard to pin it on any one thing. And it's like you want to have an entire view of the system. And I kind of didn't know where to start with that. So the first thing I wanted to go do was just generate a state map of thread activity. So not task activity, importantly, because we didn't have that information, but thread activity. So state maps are a visualization that I developed back in the Joyent days. And when we're kind of trying, actually, the origin story of this actually is a Cassandra benchmark that was performing very poorly on our Joyent infrastructure, but it was a mystery because it would perform really, really well. And then it would go through these protracted periods, protracted being like, if I recall correctly, like maybe tens of milliseconds, hundreds of milliseconds of inactivity. So you'd have like 100 milliseconds of just like the whole world stopped and then starting again. And you're like, why are we stopped? Why are we not doing work? And it was really, really hard to figure out why we were not doing work. And ultimately, the reason we were not doing work is actually because we were getting nagled. We're just ringing the chime all over the place, Adam. But it was, and we were able to see all sorts of other things in doing that. One of the things Austin was asking in the chat about, like, what was the GC times like? And I think that, this is where, you kind of, with these big complicated systems, you kind of start with these kind of knobs at the outside of it. And I really wanted to see inside of like what's going on. And so what I really wanted with this was this kind of view, and the slightly more abstract observation was that we often have got a bunch of different entities in the system that themselves are in different states over time. And you can view that as disks being in different states. You can view that as threads being in different states. You can view that as processes being in different states, CPUs as being in different states. And you want to and you want to kind of correlate that temporally, and you want to look at that visually. And so the state maps are a way of doing that. So I'll drop in a link to the actual repo. This will become the canonical repo as soon as I can find someone that Scoot controls the old joint repos to kind of hand it over. But this is this is software, and actually this is the first software in which I re-implemented in Rust, actually. So it's kind of had a bit of an Oxide origin story in there as well. But this is a visualization that I had found to be valuable from time to time, and especially valuable when I didn't know what else to do and was frustrated. And we had used it to, Dave, we used this back in the day at Joint and Samsung to visualize Postgres performance, to look at Cassandra performance. So we get these kind of big complicated systems. You're trying to figure out what's going on. One of the things that I had actually forgotten about, I over the weekend, I was going back to some of my older presentations on this. And Dave, I'd forgotten that we were getting right throttled because Postgres insisted on writing zeros to its wall when it had a new wall. Do you remember this?
Yeah,
and I'm like,
because yeah. Is this the thing where it's trying to reuse files instead of creating new ones? And then
yeah, it went to go, yes, and then it went to go create a new one, but it wanted to zero at first, even though it's like you just create a new one, you actually don't need to zero it. So it would actually write zeros into the new wall, and then it would get right throttled while writing the zeros, and everything would just cork up behind it. And then you ended up seeing semaphore wait behavior. Yeah, Adam, maybe there should be a different chime from Postgres, Postgres trauma.
Seriously, you mean Joyent was down again because of a Postgres problem? Okay, got it.
Oh, that's surprising because it's that. It's amazing. It must be the workday already.
Have I already heard this episode? No, it's different.
No, different one. Actually, different one.
I don't think we've even talked about this particular one before. There's actually at least two here. One of them, I think, was that it was trying to reuse a file, and we wanted it to create a new one, but because it was reusing it, it had to go fetch it from disk.
Right.
It's using these as empty buffers, and it doesn't care about them, so it's taking the last file that it had, which it last wrote to 15 hours ago. Sorry that I'm going down this path now, but I am.
But hey, here we listen. I pushed you in the traffic on this one.
ZFS has long evicted it. And Postgres is well, I don't really want to use any more disk space, so I'll grab this one from over here, which, by the way, doesn't work on copy on write. We're still going to use more disk space. But in the process, in order to write anything, it had to page all of those things back in. And yeah, it was a bad scene. So we were doing all these reads from disk just to populate a page that Postgres was then going to wipe out because it didn't want to put it in a new file, which made sense on old file systems, but definitely not on this file system.
Right, and then we got it to create a new one, and so it insisted on writing zeros, which also might have made sense in the 80s, but definitely did not. It's no, please don't. You're right, throttle. And it's it's also this. It's hard to blame Postgres alone because the system was already having multiple organ failure. The system should not have been in a state where it's I can't write zeros to a file without bringing to its needs. It's no, you can't. For other reasons that have got nothing to do with you, you can't. Okay, let's just say you can't.
Just please stop. It's not your fault. Just stop.
It's not your fault. I need you to stop. Exactly. But we had used state maps to explore that problem and actually quite a bit of others. I had kind of forgotten how much. It was useful in a lot of dimensions, and so this felt like a good problem for that, because we are like, and in particular, it's like the first, I didn't know what, and actually, Dave, I think because you and I were actually like physically together when we were working on this. And I think I was even expressing at the time, like, I don't even know what I'm doing here. This is going to yield nothing. Like, this is going to, I just don't know what we're going to find here. Like, what do I think I'm going to find?
But you were a little skeptical about it, but I feel like that is a good time to ask those questions sometimes when you're like, I don't know what I'm going to find. Right?
Yeah, and I think that that's it. And I think that like I am wondering kind of what questions to go ask. And like I don't, and I think this is what I've kind of realized about state maps is they are rarely going to have the answer, but they are often going to promote new questions. And especially if you're stuck, it's like you can get new questions. So I just dropped this. I guess we have yet a third chime for whenever I say SFIG, but we've got I've just dropped a SFIG in, which was the result of a descript that I will also drop in here. And so to look at this, for those who are kind of live, what you want to do is actually download that thing. And you want to actually pull it up in your browser, because you want this is a Jarek, is this malware? It's like, well, what is malware exactly? This is it's a SFIG with a program in it, maybe a big program. But if you pull that up, you will see, and this is a much more visceral appreciation. And this is the actual data that Augustus pulled off of Colo, where we've got down that left side. And if you go kind of click anywhere in there, it'll be a little clearer what's going on. Down that all of these different rows are different threads in the system. And the different color over time is showing you the state of everything over time. And this, I don't know what I was expecting, but I was absolutely not expecting this. This was like I think what is Richard Feynman's line when dropping the O-rings in the ice water and having it like crack during the hearing? Like this seems very relevant to our problem. And in particular, if you kind of pull that thing up, what you'll see is you see two different threads at two different times with these long stretches of green. That is on CPU. We are not expecting that. Like we do not expect this thing to be CPU bound. And that gets really, really interesting. And if you kind of bring that thing up and you can click in the middle of that green, and you can, Dave, one thing I added just recently that I think is going to change my relationship with state maps is just, this is stupid, but just key bindings. You don't actually have to click on the plus sign to zoom in. So you can just like, if you hit plus, you'll zoom in on the keyboard, and minus will zoom out. And then the other thing I did is that if you hit shift, if you click on something, it highlights the entity. If you hit shift and then up, it moves to the entity above it. So you can use shift up, shift down to kind of scroll through the entities on the system. And then if you zoom in there, if you do shift left and shift right, it will take you to the next state for that entity. So it is like way easier to move around these things to kind of figure out what they're actually doing. And in this case, like, why is this image just like a real smoking gun? Is like, we have got this long period of green, and in that period of green, there is nothing else happening. And if you click on kind of one end of that green and then you shift click at the other end of the green, it will highlight the actual time delta in there. And that time delta is like Augustus, you were reporting kind of 8 to 11 second kind of delays. And this really neatly lines up. So this is like, okay, I don't know what I was expecting, but I was not expecting this. And this felt like, okay, this feels like it merits investigation for sure.
And specifically what you're looking at when you look at this state map is you're looking at a work stealing asynchronous runtime, kind of not being those things for about 10 seconds every couple of seconds.
Yeah, you're definitely seeing, and for unclear reasons, right, Eliza, what you're definitely seeing is like, you've got something doing work, and this again is the thread view, not the task view, but you've got something doing work, and then everything else not doing work. And then you kind of got these other periods where then work is being done and then not doing work. And the thing is also interesting is like you can see these shorter periods of green too in there where also work is not being done. So it's like you have these long stretches, but there is something going on here. And is it because there is a resource that these other things need that compute bound thread has? I mean, what is actually going on? Dave, this is where I think we ended up using speculations again, because it sounds like you'd already used them, but used speculative tracing, and I'm going to drop a descript into the channel there of using speculative tracing with the profile provider, which I'd actually not done before, to try. And the idea here is like, okay, this is actually an easier question than the one you were trying to answer, Dave, with speculative tracing. What you were trying to answer in speculative tracing, just to kind of back up a little bit, speculative tracing is effectively a way of just reducing the trace data that's moving through the system by saying like, look, I don't know if I'm interested in something at the time. I only know that I'm interested actually after the fact. The motivating example for it way back in the day was a program where this is cruel. It ended up being, of course, an OS bug where literally 1 out of every 10,000 mmaps would fail with enval. And if you know anything about mmap is the system called to create a memory mapping. You're like, oh well, enval. Like, how many places return enval? Like, and okay. What are some other ideas for figuring out what's happening? Because it's like, oh, there are like 4,000 places that can return. I mean, it's just terrible. It's all overloaded in the eval. It's like you got 6 different arguments, and they've got all sorts of ways to be invalid. And it's like you actually want to kind of instrument everything, and then only decide like, oh, I'm returning enval. Now I am interested in all that stuff that I traced. So you still have the enabled probe effect. But you are really reducing the kind of the cognitive load in terms of processing this to the stuff that is interesting.
But not just the cognitive load, because as you're saying, it is possible to just dump everything out and sift through it later.
Yeah.
It's possibly, it may be possible to dump it all and sift through it later, because it's not in a format that is really default very easy to run that kind of query against it. And even then, you're dumping out. You may overwhelm the system just in terms of the data that you are trying to squeeze out of it. So it's for sure. It certainly reduces human cognitive load, but may also just be enabling in the use case.
Yeah, that's right. And this is one of these things. And I think there are a couple of things like this in dtrace. It's like if you don't need this, you just kind of like stare blankly at it, being like, "What the hell is this?" But when you do actually need it, you do kind of need it. And Dave, you've been using it earlier to try to ascertain what had happened when you were off CPU, which I think is harder. But now we actually want to use it to ascertain what we did when we were on CPU. So in this case, what we want to do is like, all right, we're going to fire a profile probe that's going to fire, 1,234 times a second. If we have an active speculation for that thread, then we're going to record a stack backtrace. And then when we actually go off CPU, if we've been on CPU for what we think is like a notably long time, we're going to commit that and we're going to see all that. And Dave, you were looking at the output of that. It's like, that was pretty interesting.
Yeah. So the stack traces that we got from that were all the same thing, which kind of makes sense. And it was a background task that runs in Nexus that we call the external endpoints background task. So its job is to look at all of what we call silos. So just backing up a tiny bit. Silos are what they sound like, a unit of isolation in the Oxide system, and each one winds up having its own API endpoint with its own DNS name. And so, but they all end up pointing that the A records for those DNS names all wind up pointing to the same set of underlying instances, and we use HTTP and TLS level stuff for figuring out which endpoint you're trying to talk to. But in order to do that, because they all have different DNS names, they also potentially have different TLS certificates. So in order to figure all that out, we have this background task that queries the database and says, what are all the silos that exist, all the DNS names that I need to be operating, and all the TLS certificates that exist. And it assembles a data structure that it can use to quickly figure out when a request comes in, which certificate should it be serving and what silo should its operations be constrained to. based on the DNS name. And the whole point of this thing...
Yeah, it's strictly a background task, right? This is like a background task to enable us to move fast.
That's exactly right. The whole point of this thing is to take all that complicated calculation and stuff out of the request path. By doing this in the background, we do it like once a minute, and anytime we know things have changed. Even once a minute is way too often, but it basically assembles this thing outside, no locks held, no anything, just like fetches this stuff and then uses Rust watch channels, which are super nice for doing stuff like this, which is basically, everything that needs this has a watch receiver for this value. And there's one code path that needs to change it once in a while. Could just send an updated value to all those things. And anyway,
cool.
That's how it is supposed to work. And that is how it works. But this thing was spending an enormous amount of time on CPU. And
it's like, okay, not a surprise that it's like we're doing some CPU work for this. Definitely a surprise that we're not doing anything else, apparently, because we're doing this. And then August says, this is where you realize, like, actually, there's another issue on here. We actually just have too many certs on this thing.
Yeah, not like a little too many, like a lot too many. Yeah, we had a renewal issue where we kept writing certificates that we thought were valid, but were not. And I think we got to like close around 10K or so. So that it's way more than we expect given the number of silos, and we knew that. Ironically, I'd run into that prior, like midway through the day, just because our certificates were expiring, and I was like, oh well, it's time to go renew them and fix a couple of these silos. It didn't really happen until I was like 25% through fixing these, that we got the spectral tracing, which those two things were just top of mind at that point then, and it seemed very suspicious.
Then also you're like, wait a minute, this would also make sense because this now correlates to when we kind of began to see this on Colo, what we kind of correlated when we had this kind of explosion in certificates. And so on the one hand, we're kind of, and then I think at that point, you're like, okay, I can get rid of these extra certificates that we don't need, and we can see if the problem improves.
Yeah. So that was like nicely an easy thing for us to do. After all of the difficulty of getting data out, like removing the invalid certificates and just testing the system again. And we saw real, like, at steps as we went down, the delay that we were seeing, the latency we were seeing was continually going down to the point where it was not exactly gone, though. We still had like around 500 to 700 milliseconds of delay, but like that's much less noticeable for a user who's like just clicking around. It just feels like a slow request, but that's still unexpected in the system. Like, there's no reason that a handler should just sit there for nearly a second doing nothing, from what we can tell.
Right. So the problem did not completely go away. It kind of ameliorated to the point where, like, okay, this is, and I think in particular, it was good to get some confidence that, like, feels less likely to be a regression. I mean, you don't want to be too speculative about that when we don't actually have it to root cause, but this feels like this is less likely to be a regression. And we can kind of deal with the immediate problem in Colo, but now you've got the problem of like, wait, what? How? Because Dave, as you were saying, like, this is like like, these things are not related. Like, this can't be causing that. I mean, it is obviously. There's obviously a causal relationship here, but it also makes no sense that there's a causal relationship here.
Yes, both halves of that are true. This makes no sense, and the data that it is related is extremely compelling. And it turned it from, this is an incident in our production system, to, okay, the production system is now fine, and we've got a pretty good idea that this is, I mean, as you said, not definitely, but probably not a regression, and probably pretty reproducible.
Right.
By loading up a dev configuration with the same stuff. And so it kind of changed the tenor of how we were approaching it at that point.
Yeah, and not that we would have ever done any different, but I do love the fact that, like, of course it would be tempting to be like, okay, well, we fixed the problem on Colo. It's like, no. Now we've, I mean, great that the fire is out there, but now we've got something that we can use this information to actually reproduce this, where we can actually completely understand this. Like, we are emphatically not done with this problem. This problem is because we understand things about it, and we understand enough about it, importantly, to reproduce it, but we're definitely not done. So, Dave, you started to reproduce this on one of our Racklet configurations, right? We've got a couple of dev systems which are smaller configs that we are kind of smallest possible racks that we call Racklet. And because I think you were reproducing it on Racklet, right?
That's right. Yep, I reproduced it on Dublin, which is one of our Racklets, and it was very readily reproducible. I wrote a script that installed 10,000 certificates, because that's what Augustus had said we'd had, and was able to see the same. I didn't do a state map, but I saw the same pattern of looking at CPU utilization per thread, and one thread would go on CPU at 100% userland CPU time for like 10 seconds. And during that time, HTTP requests were taking a pretty long time, and they were totally fine otherwise. So it was the same set of symptoms that we had seen in Colo. So I had a good feeling like we'd reproduced not just the symptom, but I mean, probably the same problem.
Great. And the nice thing about it being now on a dev system is we can now actually iterate and we can throw new software on there. And in particular, Eliza, you'd kind of seen this the previous week and had an idea of how we could better instrument Tokyo to answer Dave's questions.
Yeah, so that's right. Dave had just been asking me these kind of uncomfortable questions about Tokyo, I think last week. And this week, I started in my copious free time kind of thinking about what can we do? And one of the things that I reached for is Tokyo has, in its unstable features, it has these, I call them runtime hooks. I'm not actually sure if the Tokyo documentation calls them that, but they're callbacks that you can set when you're constructing the Tokyo runtime that it will fire when certain events occur. In particular, it has ones that fire before and after it pulls a task, like when the runtime worker thread starts to pull a task, and then when it finishes. And then it has callbacks for when a new task is spawned and when a task terminates, and those are given the task's ID, which is sort of an opaque identifier. And then there's some other stuff related to the lifecycle of worker threads that that aren't directly relevant to this, but that it also gives you. And I thought, we could at the very least put dtrace probes in there, put USDT probes in these, and they could, tell us at least when we start pulling a thread and when we stop pulling a thread. You can then set a thread local in your dscript that says, when you start pulling a task and you end pulling a task, you can set a thread local in your dscript that says, this is the ID of the task that I'm pulling. And then you can correlate every other probe that happens on that thread with which Tokyo task it's actually in. Now, there's some information that is kind of missing from this because these only get these numeric task IDs and not really any information about like where in the program those tasks came from. But so I showed this to Dave and I was like, hey, Dave, I've been working on this thing. It might be useful for you.
And this is one of those where, we talked about before, we kind of do demos on Friday. This is one of those where it's like, we cannot wait for Friday to the demo. This is like, sorry, I mean, the showmanship is a top priority at Oxide, but it's not the top priority. And there are times where and this is where we actually need to stop the clinical trial and actually just distribute the actual, the drug. And Dave, you're like, I don't want to spoil anything that Eliza might have in mind on Friday, but we have a great crate here that's going to allow it.
Well, I did show it to Dave in DMs because I wanted to be able to surprise someone on Demo Friday.
Yeah, sorry, I hope that someone was not me. But I was still surprised though. I kind of feel it's like it's always a surprise. It was Demo Monday. It was great, or Demo Tuesday. I can't remember what it was. But and
Eliza and I had been talking about it because this was like a week and a half later. I think it had become less urgent, but we still obviously wanted to do it. And we've been talking about it, and then the PR went up, and then I don't think I told Eliza that the thing I installed on the Racklet was the branch from her PR, so that I could. I was like, well, this seems like it'll probably be pretty useful.
Yeah, absolutely.
It really was the let's not wait for the clinical trial.
No, we're not going to wait for the trial to complete. The other thing that's important, and Dave, this was you were giving me a very helpful primer in terms of Tokyo parlance versus maybe what kernel parlance is. Eliza, when you say polling a task, that is not polling on, for example, file descriptors waiting for something to do, the way it would be in the operating system. When you are polling a task in Tokyo, you are executing that task.
Yeah, it's kind of the opposite of that.
Right.
I assume that the name comes from using poll in non-blocking mode. And it is like you're calling poll and finding out if there's anything to do.
Yeah.
But if you're just thinking about it in the usual blocking mode, it's the complete opposite, right? It's
the complete opposite.
This is when I do the compute stuff, not the blocking stuff.
This is when I do the compute stuff, when I'm polling, which is fine. Actually, I'm it was actually just very helpful to have I can deal with the nomenclature shift, but just a very important nomenclature shift. And this is huge because this allows us to really now begin to correlate what Tokyo task is doing what. And there's still, as you mentioned, like there's still stuff that we would like, but now we can really begin to see what's going on from a Tokyo perspective, in addition to from an OS thread perspective. So I've got fittingly another state map here. That I just dropped into the chat. Folks can go look at that. And so this is showing the result of, Eliza, this is running with your crate, so with the Tokyo probes, and with a script that I'll also drop in here in a second, that is generating the kind of the raw output for this. And now what we have on that y-axis are not threads as they were with the previous state map. These are now Tokyo tasks, which is awesome. So we can actually see now, on the one hand, and Eliza, you mentioned this, like, okay, these are just like integers, but hey, an integer is a start. We can actually correlate. We don't know exactly what they're doing, but this is actually really, really helpful. And in particular, if folks pull up that state map, and you can see now that this is running over to the core. Dave, this is running with the workload that you had on there, and we knew we would hit this, once a minute or so. Or was that by design, that once a minute, or was that just kind of an artifact of?
Yeah,
not sure.
That background task runs once a minute, and it always recomputes everything from scratch by design. So yeah, this is a very regular problem, fortunately.
So you can see that big green in there, and if you can go to the end of that state, if you actually if you kind of click the time at the end of that state, if you just type in 5M, it will set the time bounds at the top to be 5 milliseconds. And you can see that you've got we're doing nothing else, and then we start to do other things. And in particular, if you kind of click up there, so if you look at this, we are on task 833, and then we see that we are actually task 136 is what we execute very shortly after we're done with what we now know is the certificate processing task. But the question that we had was, or the question I had, it seems like that next execution is, despite being ready to run, it's executing on that same operating system thread. And we can explore that by actually this state map is what we call a tagged state map, where I tagged whenever a task is run, I tag it with the actual thread. And if you click on that executing state, while you've got that up, you'll see it'll show you the tags for executing, including the thread ID. And then you can see the thread IDs that are actually executing. And if you click on those, it'll highlight in blue. Like, for example, we can see that in this particular case, in that first act of green, we are on thread 115, which is the operating system thread now. So now we have the task to operating system thread binding. And we can see that first bit that we executed afterwards is also on thread 115. So task 136 and task 833 were both on thread 115. And Eliza, when you saw this, you immediately were like, okay, actually, I recognize this particular pathology. Or that's the way it seemed anyway. You seemed like you had an instant recognition for this pathology.
Was that me? I mean,
I think it was, wasn't it?
We were all on this call. I think this may have been I think you said the magic word, and then I think John and I maybe both at about the same time reached for the answer to the magic word.
Damn it! What was the magic word? I don't
the
even
magic
remember
word
what I
was
said.
work stealing, Brian.
Oh, work stealing. Yes. Well, it is funny because what it did remind me of a bug we had in the kernel way back in the day where where work would be, CPUs steal work from one another, which is what you want. If a CPU is available to do work, you want it to go after work that needs to be done that's enqueued in a CPU on a CPU. But we had a bug where it would steal work up until the last thing to steal because there are for a bunch of like gnarly implementation reasons, it was really tough to steal the last thing, in part because you're potentially racing with the CPU as it itself picks up the next thing to go do. So I've seen these kind of failure modes before where work does not get stolen properly. And I guess it was just me. I guess musing about that was just like the magic words for you to recall particular behavior in Tokyo. So do you want to describe that?
Yeah, so Tokyo has this optimization called the LIFO. I pronounce it LIFO. I'm going to get in trouble for this. LIFO, right?
I'm pronouncing things
the last in, first out.
Yeah.
The last in, first out slot,
There you go.
which I will be prohibited from spelling out ever again. And the idea of this optimization is it's sort of an optimization to improve performance in these sort of actor systems where there's like a lot of message passing between Tokyo tasks. And what it is when a task on a given worker thread wakes up another task, right? Such as by sending it a message through a channel or something, that task is put in a special slot on the same worker thread, and then it will always be the next task in the queue on that thread until another task is woken. So the idea is that if you send a message to your buddy, and wake him up to then pull that message, he gets to go next before all of the other stuff in the queue. And this kind of improves latency, especially in the case of like the last thing that task did was wait to receive a message, and then it maybe just like finishes up and dies, or finishes and completes and like writes out the rest of its bytes or what have you. And that just makes that happen a little bit more quickly without having that task sit all the way in the end of the queue.
And we do a very similar optimization in the operating system, Eliza. You might be aware of this for doors. So when you make a door call to a door server, you, instead of actually enqueuing that thing to run, you give it your time. So
right.
you then just become it effectively. And which I always thought was kind of clever because like, look, I am making an RPC call. This might be really quick and then it might be done and then I can run again. So I can, why not just like, as long as I've got the CPU, like I want to run this thing over here. And it's kind of a similar-ish idea where we want to optimize between this kind of ping pong use case. So there's like reason to do this. Like this is not a wholly unreasonable thing to go do. But there's some important asterisks on this behavior.
Yeah, there's one specific thing about this slot is that the way that work stealing works in Tokyo is that you have this queue of tasks that are like notified, that are in queue to run on a worker thread. And the way that work stealing works is the other worker threads, when they are bored and have nothing better to do with their lives, come around and commit crimes by stealing tasks from that queue. And they don't steal tasks from the LIFO slot. So that's interesting.
So what that means is if the thing that we want to execute, which is going to process our claim, is in the LIFO slot of a thread that is actually executing our compute bound task, it's going to execute for tens of seconds. That work is not going to run for tens of seconds, which is sad.
So that's kind of bad.
That's kind of bad. Yeah, that's kind of bad. Fortunately, it is tunable.
By turning it off.
Yeah, you can turn it off.
You can tune it all the way down.
You can tune it all the way down to off. And Dave, I think that was a relatively straightforward experiment to run, right? I think that was the
Yeah, it did require a rebuild, but at this point we were on the dev system, so that was pretty easy to do. I can't remember if we did this before or after we figured out why that would be enough to cork the whole thing. Because it was, for a while, it was still unclear, like, how does that cause the whole thing to be corked?
If memory serves, we were not sure. Like we were pretty iffy about this, and we also went down. John, in particular, who's not with us tonight, was investigating some other behavior or some code he saw in the work stealing in Tokyo that was weird. John is still alive. To clarify, he's just not on the podcast.
Of course, why would you volunteer that information if that would be wait, now it looks really weird. But so John, and actually that's an important point, Eliza, because John was kind of exploring this idea of like how, like, what is the behavior of the system when I've got something that's compute bound and something else needs to run, and he's discovering it's like, oh, this thing, there are some pathologies here.
Yeah, so he noticed some code in the work stealing code that where you're calculating the number of tasks to steal from another thread, it does a division, and he noted that means that if there's a single task in the queue of another worker when you are going to steal tasks, you won't steal that one. Similarly to what Bryan was saying about in the Lumos kernel, it also will not steal the singleeth is a word now. The only remaining thing to run in the queue, because then you race with the thing that's actually going to go do it. And so he was wondering if we might be in a situation where there's only one thing in the queue, versus the problem of we have this LIFO slot that is where the task that needs to run is.
Right. And so he's kind of discovering those issues, and then and Dave, I'm you may have already linked in here, but I did want your complete analysis as you're connecting the dots, because this is where as I recall, like you and John were kind of going back and forth on hypotheses about how this behavior could back up the whole system, because that was still a slightly open question. And what was your kind of the thought there in terms of how these things could all dogpile?
Yeah, so if you were just listening to this as we've said it so far, it would be, I think, a little surprising that that we got so unlucky that the task that was sitting in the LIFO slot was so critical to forward progress of the program, right? Because like that could be anything, and there's a zillion other things that we do, and like this problem is so reliably hit. Like, why would we continue to keep hitting that? But that was not random. And so in parallel, I think with the state map stuff you were doing that morning, I was also doing, this is when I was using Eliza's probes to keep track of the task ID per thread and combining that with the drop shot probes that we have and saying, well, okay, so this is the request, this is a specific request I'm watching that I have induced that I know took 9 seconds, and I have a request ID for it, and I'm going to watch what it's doing, and this is when I was using the PID provider. And we were able to see what it was the task was doing when it woke up right after this task that had just been on CPU for a really long time was doing. Right? Did that make sense?
Yeah, absolutely.
And the thing it was doing, like, I think I had seen this before and it just hadn't hit me how important this was. But it was doing, like, it was calling like one function, and it was basically it was a call into Corb to release the database claim. So the way this code is structured, the background task that we were talking about, remember I mentioned that it fetched a whole bunch of stuff from the database, which probably took, I don't know, could have taken a little while because it was fetching a lot of stuff. And then it released that claim. It actually probably did that a few times because it was making paginated requests through a large number of records in the database. So take a claim, release a claim, take a claim, release a claim. Finally, release the claim, and then it would go on CPU for a really long time. But that releasing the claim, that drops an object that sends a message over a channel. Something needs to read that message over that channel and then put that connection back into service in the pool. That's fine. That's the thing that wasn't running. So that claim was never being released. But that too isn't obviously enough to cork up the whole process, because we have plenty of connections. So the fact that this connection is effectively used for a lot longer than it should have been shouldn't have been that big a deal. And that the problem relates to a different code path in Corb that Sean had identified like when we were first looking at this in Colo, as like I don't see how this would be related, but if we got stuck at this point in Corb, the whole pool would actually be corked, because what Corb is doing is, in this case, we've got 5 different database backends, and we're going to maintain some number of connections to each one. And so when you go to the Corb pool and you say, I want a connection to the database, it goes to what's called a slot, slot set for each backend, and says, do you have any connections? Do you have any connections? Do you have any connections? And it expects each of those to respond promptly. It's sending a message over a channel being like, do you have any connections? And it's getting a response back that says, yes, I do, or no, I don't, or whatever. Here's the status of this slet. And it's expecting that
It's not going over the network, not blocking on I/O. This should be like instant for all these things.
Exactly. And that's the task that wasn't running. And it wasn't running because it was in the LIFO slot. And it was in the LIFO slot because we had just released the connection that was going to trigger that thing to go do something. And that's the whole chain.
Oof. So we will be disabling the LIFO slot.
Right.
That is not an optimization that we choose not to have that optimization. At least not while the work cannot be stolen out of it. It's not necessarily an unreasonable optimization, but the opacity of when this cuts against you makes it really, really tough.
We're not the first to be bitten by this thing. There's actually there's a reason that there's now a knob to turn it off.
Yes, we should be grateful for that someone else had hit this beforehand. Yes,
but not a reason to document in detail how one would infer you were being bitten by it.
To be honest,
it's documented pretty well, honestly.
Is it? Oh, good.
It is. It's just like it is really hard to know when you need this, and I think this gets into and I think there's some reasonable discussion on the issue, being like, this is really hard to know when a system is going to hit this. It's kind of like a halting problem hard.
So it does get into this sort of I would say ideological debate of how much compute bound work is acceptable to put on the async worker threads, right? Which a lot of people have opinions about, and the misoptimization here is specifically happening when a task on an async task on an async worker thread performs a relatively large amount of compute bound work without yielding.
Right.
Which the party line is generally from Tokyo is generally don't do that. Right. And instead that should be run on a blocking worker thread. And so this is kind of a tricky thing because it's difficult to know in advance how compute bound is this.
I believe that my observation was, and this is where it did remind me of the async cancellation issue, where to construct an argument that the programmer is wrong here, the kinds of arguments you're going to construct are going to look a lot like arguments that defend memory unsafe languages.
Yeah.
And it's the reason that we actually, it's not about, it's like it's a mistake to kind of go to programmer sophistication or lack thereof because it's very hard for even an arbitrarily sophisticated programmer to know that they're not going to end up in this situation. They're not going to be consuming compute on the computer. I mean, it's a computer. It's what it does.
Oh yeah, absolutely. I mean, this is something that overall I find that the Tokyo documentation is pretty good, and a lot of work has gone into making it pretty good. This is a specific thing that I don't really agree with for that reason. This specific guidance. I think there are cases where it certainly has improved latency for people quite substantially when they know that they are going to be doing, I have to go do some really heavy MPEG processing or some really heavy cryptography. I'm just going to go and do that in a dedicated thread. That has, that's often not a bad idea, but I think the danger is that there's a difference between maybe doing this will improve latency for async work, and like maybe you want to do that because it will make things faster and more responsive, versus this problem of like you can actually block the runtime for a really long amount of time if you forget to do this, right? So it's sort of like it maybe is good advice in some cases, but it's not a defense against like, you were holding it wrong when it goes and behaves badly.
Yeah.
Well,
like yeah. Go ahead, Dave.
I'm gonna try to make an argument for the other side of this, which is like, in this case, we've got 10,000 TLS certificates, and that's taking 10 seconds to parse, and that's obviously bad. But what if we had one TLS certificate? Is that too long? And if that's too long, what about the JSON objects that we parse in our HTTP handlers? And what about the HTTP parsing, right? And the more parts of the system that you're punting out to some other thread pool, now you have to wonder about, how do I size that thread pool? And how do I balance the number of threads it gets against the threads that I give to the async workers? And it's a much harder problem. And if the problem you're worried about is starving an async worker thread that will no longer be able to run other stuff, that's not really a problem, right? Even this 10,000 certificate thing, like it's a very nice and easy model for us to say, all the CPUs that we want to give to Nexus, they're all in the async worker pool, and we're going to just run all our compute stuff in there, and that's fine because we have a ton of CPUs. The problem here was the specific case that what I just said is predicated on the assumption that if there's work to be done and idle workers, then the idle workers will do that work. And that's where we got burned here. But it really feels like an exceptional case to me. And like the idea that we should try to proactively identify the stuff that might take a lot of compute time, that it just seems intractable. I mean, we talk about it as async, but all this stuff is using compute. That's what it's doing. You know?
Yeah.
Just to be clear, I think that like where that advice is coming from, I think is intended for programs that have a very strongly bimodal distribution kind of by design. Like you're writing a server that processes a bunch of HTTP requests, and then, occasionally those HTTP requests cause it to do like something that you always know it will be, parsing 10,000 certs and never stopping to do IO in there. And the advice is like, maybe you should just go separate those two things because you have those like two sort of halves of your workloads and you would like to continue serving requests during that time. I think that it is being taken way too far to go into this sort of idea of like all compute bound or temporarily compute bound workloads in a program that's doing all kinds of different stuff, should always be punted onto this other thread pool.
Well, it kind of reminds me of like the arguments for processor sets, where we can take groups of CPUs and we can group them into processor sets, and those processor sets will only run the work that's bound to that processor set. And it's super useful if you've got like hard real-time work, or you've got like you want to more statically define the way the system is scheduled. That's great. Like they're a really good tool to have, but the recommendation can't be for everybody to run processor sets, because then you run out of processors, right? You're using the resource so inefficiently. And Dave, as you're saying, it's like the advantage of async is that your use case should be a shining example of why it's a great idea to have a shared thread pool. Because it's like, hey, we've got this async work. It's not very important. In terms of like, no one's blocked on it. So we should use this available resource we have in terms of this thread pool, provided that we don't have more work to do than we've got threads in the thread pool, which should be great. Eliza, another question that kind of, and we were definitely braced for, because we didn't use Tokyo Console for this, but Tokyo Console is great, and I love the visibility that it gives you, but it's not necessarily a fit for this problem exactly. What's kind of your take on Tokyo Console? From my perspective, it's like one of the challenges is just not really geared towards production as far as I can tell, but that this is where I'm kind of out of my depth.
Do I have to go get my lawyer?
No, it's fine. No, we're just sitting down having a conversation. You don't need to make it complicated.
Well, one of the biggest problems with Tokyo Console is, and you are correct that it's one of these things where, I certainly tried to make its overhead not the worst, but it costs a lot to collect all of this information.
Yeah.
And in particular, the reason it costs a lot is because of this problem that we were talking about earlier in these async systems, that it's kind of like a lot of the information that you want is no longer known by the time the task is running.
Yeah, interesting.
You want to know where in the program it came from, because that sort of tells you, like, what does this actually represent? This like sort of opaque object that the runtime has decided to put on the heap, like what code does it actually represent? And it's like kind of difficult to determine that unless you know where it came from in the program. And that means you have to sort of proactively collect this information. And this is kind of the same as what you were talking about with speculative tracing, right?
Yeah.
It's that genre of problem where, you know, you kind of need to know, like, what's this thing? And you need to collect that information now because you might want it when you're actually trying to debug a problem. And
Right.
so the console, because of that, does have this sort of problem of you're introducing a bunch of overhead to collect all of this data that 99% of the time in production you're not actually going to want. So it's hard to avoid that. And there's also, you know, it's intrusive instrumentation that has inherently kind of more overhead than something like dtrace, where there's basically nothing happening until the information is actually desired.
Right. In other words, the disabled probe effect of Tokyo Console is non-zero. So
yeah,
as much as we might want it to be as low as possible, just the reality is because the information it gives you is extraordinary, but it does require work.
Yeah, and it also would not have caught this specific issue with the LIFO slot. However, something I do think is like kind of nice about Tokyo Console, and that maybe is like worth considering now, is that Tokyo Console has a notion of warnings that it essentially does sort of like runtime linting. So it'll look for patterns in the program, and this is part of what motivated its development, was that, you know, Tokyo is sometimes difficult to use correctly, and that there would be a lot of sort of common recurring issues that people would show up with, and sort of being like, you know, why is my program slow? And then it just turns out to be sort of something that we've heard a million times. And there was so like one of the features that the console has is it'll tell you, it'll just sort of watch for various behaviors, and it'll give you little like warnings while the program is running. Hey, this might be a problem. This task has been compute bound for a really long time, or so that it would have caught that part. Or this task the future for this task was very large, and so the runtime had to box it because it would have overflowed its stack otherwise. Maybe you have like a buffer, you know, that you're declaring inside of an async function instead of on the heap, and it's making your future too big. And that makes spawning it slower because you have to mem copy that whole future, or, you know, things of this nature. And then it gives you these like little warnings that's sort of like, so we don't know that this is a bug in your program. They're like compiler warnings, but it's something you might want to take a look at. And so a lot of the time, the guidance that we would give people with this is, you know, don't run it in production, but instead run your software in development and look at it with the console and see what it flags. And so it probably could flag issues where something has been, you know, because it has with additional instrumentation of the runtime itself, it could flag things like, hey, a task has been sitting in the LIFO slot for a really long time.
Yeah, right.
Suggesting that you are running like substantially compute bound work on the same worker thread, and you're having issues like this. But it wouldn't have helped us debugging this problem because it would have had to be there.
Right. When this is what I think just highlights the fact that it's a great tool, but it's a different tool. It's a tool with a different use case, which is an important use case, but great for that kind of development use case. But when it went on these production systems, and when the async elements kind of misbehave, we really need. And then Eliza, obviously, the Tokyo dtrace crate is awesome, and I think you'd highlighted some other things that the instrumentation in the Tokyo runtime itself where we can get, and I think we've already lurched a big step closer, but we can kind of live that dream of being able to get total visibility into what's executing and what's not executing and why, and being able to correlate that across the system. And I think for us, I mean, Dave, we have, and we did verify that we turned this off. We turned off the LIFO. You almost had to say LIFO optimization, Eliza. I suppose if you honor Svig, I guess I will say LIFO. We turned off that optimization, and we saw the behavior that we wanted to see.
Yeah, that's exactly right. And yeah, that was very compelling data point.
Right, and that's going to be the fix for us, at least for the moment. Like that's going to be something that we're going to be, we will be disabling that for Omicron.
Yeah,
and I pointed to your full analysis there, but this was an odyssey. We fortunately one, Dave, that was shorter than the last odyssey. The like feels like 3/4 of a year odyssey you were on the last time you were talking about a debug odyssey.
Yeah, that was a lot. Yeah, that was rough.
with Cockroach, but this one was not dissimilar in that we had this thing that, boy, did the symptoms of this were far removed from the root cause. And it was kind of a complicated chain.
Yeah, and fortunately, a big difference too is that we have a lot more control over the instrumentation in this system, and we've already made a bunch of changes and plan to make a bunch more changes to make this stuff a lot more instrumentable. Something that is hitting me hard the more I think about this is like if this had been a threaded system, we would have taken a core file and we would have looked at stacks and we would have understood the blocking chain at least like in a minute, I think. We wouldn't have understood the delay slot, the LIFO slot problem yet, I don't think. But we would know what tasks were blocked on what. We spent so much of this time on that.
Yeah.
And we were trying to figure it out dynamically. And we've added a bunch of probes, but I think there's still some probes we'd like to add to be able to... Like Eliza, there's no Tokyo hook yet for task wake up, right? Like task A woke up task B.
But
that would be a big one.
Really
that'd
nice
be awesome.
To have.
Yeah,
and
that'd be awesome.
That's something that there actually is a tracing event that the Tokyo console uses. And so if there was a way to glue that into dtrace or to add a hook for that so that we could emit a dtrace probe in wake-ups, that would be really nice.
Yeah,
that would have allowed us to...
The wake-ups are supposed to be like very few instructions, and sticking a bunch of code in that path is going to have some overhead. And actually, I think ideally we would just have a USDT probe in the runtime.
Yeah, right. Right.
Because it's like we would really like that to be as minimal as possible. And the other thing I was going to mention, which I see there's a question about in chat, is this wouldn't have happened in a threaded program because threaded programs have preemptive multitasking. Right. And this is like a problem this is specifically like why you might want to have preemptive multitasking.
Oh, yeah. But as I hasten to point out, we have had problems in the past that we did fix that looked a lot like this. And so I think you can also argue that like, well, this is just kind of this is part of the maturation of a system is getting to not just these issues, but being able to get the kind of the surrounding infrastructure to be able to debug them. So it's not hugely surprising that we hit something like this, but I thought it was great that we were able to, Eliza, that you were able to turn around so quickly with the Tokyo dtrace crate was amazing. And Dave, that you were able to deploy it quickly. I just feel like we were able to very quickly get to the bottom of this, which was really terrific.
Yeah, once we reproduced it with those Tokyo probes, I think that was incredibly valuable for that. That was really helpful. Another thing that I was thinking coming out of this, something like task microstates, similar to the way we have thread microstates.
Yeah.
If we'd had that, so the Tokyo task wake up probe I was describing would help, like a core file, would allow us to understand the parts of the blocking chain that weren't the LIFO slot, where the HTTP request was blocked on a connection, the connection was blocked on some status from this thing is blocked on whatever. That would have the last thing I think we would, it's hard to reason about what that would look like in a threaded system. But with the task wake up probe, we would be able to see those same connections by tracing that and looking at the stack trace, right? But if we had task microstates, we could also look at the state that's like, how much time is this task spending ready to run but not running, right? There's a thread microstate for that. I forget what it's called. Wait or lat. It's the lat microstate, right?
Right. Yeah, that's
that
right.
would have been a smoking gun. It's like
So
this thing is ready to run and has been ready to run for 9 seconds and is not running.
That's something that we have in Tokyo Console. And I think it's something we probably could figure out a way to get in dtrace instrumentation as well.
Yeah, that'd be great.
That would be cool.
That would be huge. That'd be huge. I mean, I think, and we made the system better in a couple of different dimensions here, which is exciting. So this was a good one. This is definitely had the village in on this one. And Augustus, thank you very much for. I mean, you were definitely the first on scene here, and as you've done so many times before, thank you for all of your hard work. And we had a lot of folks involved, John and Sean, and obviously Dave, you and Eliza, and it was this was a good. We always come together for debugging. It's always great.
Yeah, Dave and I were talking about this on Matrix earlier today, and we discovered that we both share a favorite movie, or one of our favorite movies, Apollo 13. And the way that we debug these bugs at Oxide often makes me think of Apollo 13, because there's this sort of like culture at NASA of the like flight controllers in mission control, and then they have this sort of back room that's full of all of the engineers who like design these various systems, and they can kind of pull those guys in for advice, and get sort of the domain expert on like this particular part of the spacecraft or whatever. And sometimes the way that we solve problems at Oxide is a lot like.
I know what you mean in terms of like being able to quickly pull in all the domain experts. And then it is really, and Dave, you were, I know, drawing the analogy to years and years ago when you, Ryan, Dahl, and I were looking at a misbehaving node process, and the three of us had no idea what was going on. And when we ultimately root caused it, we just realized, like, boy, do we need better instrumentation here? Because we had the person who wrote Node, the person who wrote dtrace, or one of the people who wrote dtrace, and then the person who wrote the code that we were trying to debug, and the three of us couldn't debug it. It's like, okay, we obviously need better instrumentation here, or what have you. But Eliza, that's a very good point in terms of like the ability to pull in everybody very quickly, which I'd like to say. And let's go ahead and ring the chime one last time for the RTO or GTFO episode, which Adam, I've been linking to like a decent amount actually, because I feel like this is one of these great strengths of a remote team is that you've got an issue like this, and all of a sudden, you've got a Meet and you've got a Google Meet, and you've got all of the experts are like right there. You've just kind of conjured them out of thin air, and everybody is beginning to iterate quickly on hypotheses and questions we want to ask of the system. It was good stuff. And we definitely knew, I mean, when we nailed this on Friday, I'm like, and we've got a podcast episode for Monday. This is, we've done it again, folks. We have generated the content that we all know that the computer company is really just a ruse for generating content, and we did it again. So great work. And yeah, Adam, sorry, I didn't even float this one past you. I knew we were. I definitely.
I saw this one coming. Yeah.
You said you're like, well, another week. Well, I'll tell that I keep calling Morris Chang in for the TV speculation bug episode, and it keeps not happening.
Yeah.
But next time, Morris. Next time. All right. Thanks, everyone. And thanks again, Augustus, Dave, and Eliza, for joining us. Thanks, everyone. Talk to you next time.